Hi all. In this video, I'm going to talk about our research one-bit distributed mean estimation with unknown variance. In this work, we will consider the statistical parameter estimation problem. In this we have considered samples are distributed among the users and server want to estimate some parameter of interest theta in the form of theta hat using the shared information from the client. And here assumptions are samples are i.i.d and distributed among the users, and each user can send limited number of bits. So here we are considering communication constraint as a bottleneck. So in this paper, our design objective are, so we have considered x1 x2 xn are i.i.d, and the samples are coming from a PDF fx mu sigma with unknown mu and sigma, and mu is a real number and sigma is positive. So each encoder map the samples xi to one bit of information. Xi is either 0 or 1, and our design objective and goal is to design a protocol that minimize the mean square error, and we analyze the asymptotic performance of this protocol. So in this work, let me briefly summarize our main contribution. So before that, let me define the scale location family. Let fx denote a zero mean with a unit variance on R, and the associated scale location family can be defined as using equation 1. Here mu controls the location and sigma controls the scale relative to the baseline density. So we can control a scale and location. That's why altogether we are referring this density function as a scale location family. So now it's a good time to briefly summarize our main contribution. So our main contributions are as follow. First, we design simple non-adaptive and adaptive one-bit protocols that derive corresponding to upper bounds on mean square error. Second, we derive lower bound on mean square error for both non-adaptive and adaptive protocols. And then third, by matching these upper bound and lower bounds, we establish the optimality of our proposed protocol. Finally, we demonstrate a strict performance gap between adaptive and non-adaptive scheme for a broad class of symmetric, strictly log-concave distribution. So now I will talk about estimator for a scale location family that we have uh, used in our work. So we consider two class of estimator for scale location families, non-adaptive, where each sample encoded independently without using information from other users. So here y of I only depending on xi, and the estimate is from using all the encoded bits. So now we are moving to adaptive one, where each sample is encoded using information from previous output also. Here we can see y is depending on xi as well as the previous output y1 and up to the yi1, I minus 1. So the final estimate is also again given by this. So it's depending on previous itself. So that's why we referring it as adaptive. So now let's discuss one by one. So non-adaptive estimation for a scale location family. In this scheme or protocol, we split clients into two groups, N1 and N2, with some fractional part. We are saying K1 and K2. And we use the quantization threshold theta 1, theta 2 to encode our sample. So we have optimized for selection of theta 1, theta 2, the optimized algorithm we have used. One can see the paper, how we have chosen this theta 1 and theta 2. So first group of client transmit which as like 1 if this xi sample is less than theta 1. So using threshold theta 1, we are encoding. And for second group, we are using theta 2 as a threshold. And then using this information, we estimate mu and sigma. So with this protocol, we have a result like achievable MSE for non-adaptive protocols. So for every mu, which are real number, and for positive sigma, asymptotic MSE for sigma, we can have this, and for asymptotic results for estimating of this mu c, the result is this one, where sigma I can be defined as follow. So now what's a lower bound for non-adaptive protocol? That's the result I have shown is not optimized. It's a achievable one, but lower bound for non-adaptive protocol is we have assumed fx, this density function, and the form of e raised to power minus phi x, where phi x is symmetric, differentiable, and strictly convex, and upper bounded by a polynomial. Then for every one bit non-adaptive protocol, this lower bound will be followed. And here T of fx is distribution distribution dependent constant, and this on the quantity depend only the baseline density. So one can note here the lower bound holds even with non-identical encoder, even if we have derived this one for identical encoders, but this will also hold for non-identical encoders. So now we are moving to the adaptive protocol, where we have divide our all users in three groups. In first two group, we just split the users, and then they use theta 1 and theta 2 as a threshold, and then they produce a course estimate of mu c and sigma c hat. And then in adaptive part, so we will broadcast this mu c to the third group of users, and they will use mu c hat, this quantity, as a threshold to quantize their sample or encode their sample. And then finally server will, using all these samples information, server will produce the final estimate of mu. So with this scheme, the asymptotic performance of the adaptive estimator, we obtain the following asymptotic results. So consider the adaptive protocol with one round, only one round of adaptation, where n1 n2 equal to n3 by log n3. This is the optimized value, and one can refer the paper how we are choosing this for getting this result. So this quantity will converge in a distribution to this Gaussian as n tends to infinity, and the asymptotic MSE will be satisfy this lower bound asymptotic results. So now optimality of our results. So to support our optimality of our result, we have established the following theorem. Let fx be a symmetric log-concave distribution such that the score function follow this is non-increasing in x and is uniquely maximized at x equal to 0. So we are referring equation 2, the expression of equation 2 as a score function. It's a more general nomenclature. Then the theorem, though this is the result what we are having for every sigma greater than 0 and mu on R, any one bit adaptive protocol for estimating mu where each xi drawn from a scale location family, then this must satisfy this lower bound. So this shows this is the fundamental lower bound of one bit adaptive protocol. This shows the optimality of our result. So now we will discuss about the communication and computational complexity. So communication cost is one bit per user in the two phase with a single broadcast. So first of all, we just compute the rough estimate, the course estimate of mu c, and then we will broadcast it to all the client in the third group, and they estimate using same scheme using this threshold, and they finally they communicate the one bit of information to the server. So computational complexity is in order 1 for the local encoder local encoding per user, and server aggregate in order of 1 bit and perform in order 1 additional computation. So it's a order 1 and order n in term of communication and computational complexity. So now we'll discuss much more about the generalized Gaussian family. We have analyzed our protocol to generalized Gaussian distribution. So generalized Gaussian distribution has a density. One can see in equation 3. The distribution is symmetric about 0 and has 0 mean with the unit variance for all beta greater than 0. If we set beta equal to 2, then this generalized Gaussian reduced to a standard normal distribution, and if set the beta 1, then generalized Gaussian reduced to a Laplace distribution. So although we are having general result, but Now we will discuss about the optimality and lower bound of non-adaptive and adaptive protocol, how it's a vary with beta, selection of beta. So asymptotic MSE constant versus ratio, and ratio versus say parameter beta. So now we will discuss if we change the beta, for what value of beta our non-adaptive protocol and adaptive protocol behave like what. So in figure one can see like this is the constant for non-adaptive one and this is the constant for adaptive one. So if we change the beta here, this the crossing will be 1.85. So if we'll have beta greater than 1.85, so our non-adaptive protocol will no more optimal compared to the adaptive one. So for this beta 1.1 to 1.85 we have seen, so this is the crossover. So if we go from beta star like greater than 1.85, so then the non-adaptive protocol, the constant of non-adaptive protocol will not more valid as compared to adaptive one. To analyze this one, let's understand by one simulation results. So so and that will be I will talk in upcoming slides. So now we will see the MSE of the function of location parameter. If we MSE versus mu. So if mu for the generalized Gaussian source and the shape parameter, we are choosing beta equal to 1.5 because the crossing will be happening at 1.85. So after if beta greater than 1.85, then our adaptive one will still valid, but non-adaptive constant and non-adaptive lower bound will not valid more after this bound. So one can refer the paper for better understanding. We have explained and we have given example properly for this one. So now MSE is a function of location parameter. So we have set beta equal to 1.5 with the unit variance and using this 40k user. So one can see its lower bound and that's MSE for the this is the for adaptive one and this is for non-adaptive one. So in all the case, we have sampled so mu from -2 to 2, even if it's valid for any real mu, but for the presentation and for illustrating our protocol and for validation, we have uh, assume that some mu is -2 to 2, and then one can see it's adaptive one will be performing much better than what non-adaptive one. So now, let's say, what if beta equal to 2? So now we have obtained the results at beta equal to it. The limiting beta is around 1.85. So now beta equal to 2. So it's a Gaussian. So one can see here the worst case adaptive. This is the worst case adaptive and the lower bound of adaptive one and lower bound of non-adaptive one here. So one can see the non-adaptive lower bound of non-adaptive one is lower than what we are having adaptive bound. So that's why we are not claiming that our non-adaptive lower bound is optimal for beta greater than 1.85. But the protocol itself, the performance of protocol is still valid. Like worst case adaptive is still beat the best case of non-adaptive non-adaptive one. So this is still performing better. One can see like average worst case of adaptive is this one, this curve, and worst case of non-adaptive is this one. So it's by simulation this validation is happening like the adaptive is performing better, but for lower bound this is loose for beta equal to 2. That's what we have analyzed in this slide. One can follow. So now that's why we have for further validation and simulation results we have fixed beta equal to 1.5, and we will just included here for the generalized Gaussian distribution with beta equal to 1.5 as a representative example. So this will be follow. Now if beta 1.5, then one can see that this is the lower bound of adaptive one and this lower bound of non-adaptive one. Now one can see it's you can observe this lower bound will be still valid. So lower bound is lower like for adaptive one, and these other scale location families follow the same behavior, and a scaling trend the consistency you can see across the strictly log-concave scale location families. So non-adaptive estimation. Now we have uh, see, we have observed that with the beta equal to 1.5, if we partition, if you do partitioning of with the different fractional values, k1, k2, then what will be happen? So trend will be same, but we will get best result when k1 and k2 will be equal. So if we divide equally in each group in non-adaptive one, so then we will get the better result. So we have to divide our users equally in two groups in non-adaptive case. So for adaptive estimation, so we have used a fraction, a small fraction of some users in two group, three groups. So, but two groups having a small number of users for non-adaptive estimation, and then the rest of the users we have used for adaptive estimation. So K1, K2, one can see like 0.05 and 0.5, so 5%. And the case that's optimal we have got. So this is the result. So this is still valid, and this is the lower bound for adaptive one. So adaptive protocol achieve the improved scaling as compared to non-adaptive. So now a general question for this is like, do more bits help? If we use the more number of bits instead of one bit of quantization, what will be happen? So we also compare, we do compare one bit protocol with the centralized unquantized benchmark, and that is given by the Fisher information lower bound. So for any estimator based on n sample, the centralized MSE has to satisfy this quantity here. This is the quantity which represent the best achievable constant without any communication constraint. And this comparison reveals the whether allowing more bit rather than one bit per sample can be significantly improve our asymptotic MSE or not. So we have simulated and we have seen if we increase the bit budget, the marginal gain we are getting, one can see here. So for this bound, this lower bound using Fisher information, so best results one can think of in this protocol, and non this is the non-adaptive one, and this is adaptive one. So one can see this gap is not too much. So the adaptive one bit bound closely approach the Fisher information limit, and similar behavior observed across all the skill location family data we have included in our paper. So now again one more question for the limits of multi-threshold non-adaptive scheme. Let's say one may think about that's a natural idea to assign different clients a different threshold. Okay, what will happen if we assign different threshold to the different client? So aggregating these one bit responses resemble the non-parametric estimation, because for each user we are having different threshold. So then for decoding we need to know that aggregation will be little bit difficult, and if we using this quantity then expectation will be like this equation 4. And a multi-threshold estimator can be formed by a Riemann. We can estimate using Riemann sum, and this will be estimated. So where each interval, this ij we are saying, is an empirical average of one bit threshold test, and each threshold is still produce a Bernoulli observation like 0 and 1. And refinement require spreading clients across the many threshold, because we are having many threshold. So decoding will be hard. So now, so bias variance, now bias and variance trade-off of the fundamental limits. So we got this result. So let X have a bounded density, Fx bounded by above L, and expectation is the finite expectation. Then the multi-threshold estimator, this satisfy this expression, where K is n by 2m, so n number of threshold we are saying. So bias decreases with kind partitioning if delta is very small, but variance is scaled by delta by K as this theta minus 2m. So for unbounded support, if you're considering unbounded supports, that's a theta m tends to infinity. So variance cannot be very linearly in order of 1 by n. So hence the multi-thresholds non-adaptive scheme cannot achieve the parametric rate for the unbounded distribution. So this is the limitation we have observed, and this limitation overcome only by adaptive protocol. So in non-adaptive, even if we use multi-thresholding, it won't help too much. So that's why this motivated us to go for adaptive protocol. So thank you for watching. This is from our side. So any questions are welcome. You may write to us, and please do read our paper. If you are having any feedback, please feel free to reach us. Thank you.